In this video, we're going to assemble the components from the last few videos into a common piece of benchtop test equipment. We need one more component to make a spectrum analyzer, and it's called a power detector. Power detectors convert signals of any frequency into slowly varying voltages that are proportional to the signal power. The symbol for a power detector includes a diode, because most of the common ways to make a power detector involve a diode. One of the most common ways is the envelope detector circuit that I've pictured on the right. This circuit consists of a diode driving an RC low-pass filter, and its operation is illustrated in the waveforms below. The output voltage follows the input voltage until it peaks, and then the output begins a slow decay based on the time constant of the low-pass filter, because current can't flow off the capwards backwards through the diode. When the input rises above the decaying output, the diode is turned on again, and the output is restored back to the amplitude of the input. If the low pass is slow enough, then the output will very closely approximate the input amplitude. A spectrum analyzer is designed to produce a frequency domain picture of an input signal, which is shown in the display in the lower right here. The way it does this centers around this ramp generator in the lower right, which controls a lot of the action in the spectrum analyzer. The ramp generator produces a ramp voltage that controls the position that we're currently drawing at, so it drives the X control input of the display. It also influences the Y value that we choose to draw by acting as the control input for a VCO. The output of the VCO gets tapped off to an optional output called a tracking generator, which is useful for making Bode plots, but a little bit irrelevant, and also driven into the local oscillator of a mixer. The RF input for this mixer is the input signal that we care about. So the result is that the input signal is going to get shifted by different amounts depending on what's coming out of the VCO. So it's going to be shifted to positions omega LO minus omega RF, with omega LO as a varying value. That shifted input gets put through a narrow filter called the resolution bandwidth, or RBW filter. This RBW filter sets the total noise power of the signal. The signal is scaled by a log amplifier to convert values to its amplitude to sort of a decibel scale, and then it's passed through a power detector in order to pick off that decibelized amplitude. Finally, the output of the power detector gets filtered a little bit and then drives the Y control input of our display. So in total, this means the Y value of the display is set by the output of a mixer being passed through a narrow bandpass filter. So we shift our input frequency, and then we use this narrow bandpass filter to pick off one little part of it, and that one little part gets displayed at a particular Y value. Because we sweep the frequency that we're picking off with the bandpass filter, we effectively look at every little piece of our input spectrum and then graph it. We'll see an example of that on the next slide. So here's an example of the mixer plus resolution bandwidth operation. The input spectrum is a signal with some noise, we've shown that on the left. And since mixers multiply in the time domain, we convolve in the frequency domain, meaning that we would get two copies of this signal, one at the higher LO spike and one at the lower LO spike. I've only drawn one at the lower LO spike in our IF signal here, but there's some symmetry arguments that show that the higher one would add up similarly. We can see that this single copy, though, has been shifted to the left. You can notice this little pattern that was right at the origin is now in our RF is now a little bit to the left in our IF. And that results in our narrow resolution bandwidth filter in these dashed lines not collecting much of interest. It just sees some noise. So this would result in a low value being displayed on the y-axis of our spectrum analyzer. However, if I increase the LO a little bit, you can see this doesn't line up exactly with our input here, with the LO on the first line. Then our signal gets shifted a little bit further. This is to the left of where it is in this IF. And that means that we get a signal falling into the resolution bandwidth. So our resolution bandwidth is now looking at a different part of our input signal because the LO has increased and shifted it further. So that means that this resolution bandwidth is going to, bit by bit, see every single part of our input signal, meaning that we can build up a whole spectrum in our spectrum analyzer. The resolution bandwidth is usually the narrowest bandwidth in our receiver chain, which means that it sets the thermal noise power that gets into the spectrum analyzer. The RBW filter is immediately followed by a power detector, so the thermal noise power in the RBW filter is converted to a voltage level in the spectrum analyzer plot. The level that thermal noise lives at is called the noise floor, and it's, like I said, set by the RBW. You can reduce the noise floor in a spectrum analyzer by making the RBW smaller. That increases the sweep time to measure a spectrum because the total number of measurements you need to take is related to the number of resolution bandwidths that cover your whole input signal, or the whole measurement range. And also because the settling time of the resolution bandwidth filter is roughly proportional to 1 over its bandwidth. The power level of the noise floor coming out of the power detector passes through a filter which is called the video bandwidth filter, and also an amplifier. And because of the noise in the power detector and noise in the filter, it's going to have a little bit of noise on top of it. It'll wiggle up and down some as you go across the display. The amount of variance on top of the noise floor is set by the video bandwidth filter, or the filter of the video bandwidth filter. The bandwidth of the video bandwidth filter. So returning to the kind of key point of this slide, being able to move the noise floor around on a spectrum analyzer is really powerful. If you shrink your resolution bandwidth, which often happens automatically when you zoom in on a signal in modern spectrum analyzers, you get a lower noise floor and can see lower power signals. So remember, one of the key tools you have with a spectrum analyzer is your resolution bandwidth in order to try to find very small signals. So in summary, spectrum analyzers use a mixer and a VCO to slide an input spectrum across a bandpass filter, which measures the power in each little filter band on our input signal. And resolution bandwidth determines the noise floor and the sweep time of a spectrum analyzer. So to see small signals, zoom in on their frequency.